Hi friends, I am Payal from Dronacharya Group of Institutions, Greater Noida. I'll be discussing about operational amplifiers. So let's start. What is an operational amplifier? Operational amplifier or op-amp as we know it is basically an amplifier which enhances any signal and produces a larger signal. So this is how a op-amp looks like. It has 5 terminals. V1 is a non-inverting input terminal. V2 is the inverting input terminal. V0 is the output terminal. And plus V and minus V are the power supplies. So what an op-amp does is, it basically amplifies the difference of the potential between these two terminals and produces a Vout. So this is mainly a differential amplifier with a single output, which means that this amplifier amplifies the difference between the two signals. So V0 is A times V1 minus V2, where V1 is this and V2 is this, and A is the open loop gain. So we've learned that V0 is A times V1 minus V2. Let's manipulate things a little. What if we apply V2 to ground and our input only to V1? So if V2 is 0, according to this formula, this will be 0. So V0 will be A times V1. Now if this is the V1 signal, so V0 will be enhanced version of V1, that is this. As you can see from these two figures that both the waveforms are in phase of each other. Let us see the other scenario. What if we apply our input to the inverting terminal and apply ground to the non-inverting terminal? So if we are applying input to the non-inverting terminal, then V1 will be 0. So in this formula, if V1 is 0, V0 will be minus of AV2, like this. So if V2 is this, V output would be something like this. If you compare these two waveforms, you will see that both of them are out of phase of each other by 180 degrees. That's why V2 is also known as inverting terminal, because it provides an enhanced version of inverted input, right? That's why this is called a inverting terminal, and this was a non-inverting terminal because it provided only an enhanced version. It didn't provide any inversion. So this is how an equivalent circuit of op-amp looks like. We've already discussed about the non-inverting terminal V1, the inverting terminal V2, the power supplies plus V and minus V, and the output terminal. Other than that, there is an input impedance Rn, an output impedance Rout, and a voltage controlled voltage device GVin, where G is the gain and Vin is basically the potential difference between the inverting and the non-inverting terminals. Now let us study some characteristics of an ideal op-amp. Let's start with the input impedance. Now ideally we want the input impedance to be infinite, because what we want is, we are basically amplifying the difference V1 minus V2, right? So we don't want to lose any potential across this resistance, and we want that exact difference to be reflected to this voltage controlled voltage device. That's why we want Rin, or input impedance, to be infinite in ideal op-amps, so that whatever input is applied across Vin should directly be applied to the op-amp. Next is the output impedance, Rout. Ideally we want this Rout to be 0. Why? Because we want the exact output which is coming from this GVin to be reflected at the Vout. That is only possible if we have a short circuit over here. That's why we want Rout to be 0, so that whenever we apply an output load, RL, the output should come across it. And we are not losing any potential across this resistance. Next comes the bandwidth. In case of bandwidth, we want our op-amps to support all the frequencies. That's why we want our bandwidth to be infinite. Next comes gain. Obviously, we want our gain to be infinite. There is no point of discussing this. Next comes when Vin is 0, Vout should be 0. By this, what we mean is that if we are applying same potential to both the terminals, then our Vin, which is the difference between the potentials, will be 0 because we are applying same potential to both the terminals. Now, since the difference is 0, so its enhanced version will be 0. So, this is what it is saying. In ideal cases, if Vin is 0, that is, we are providing same potential to both the terminals, then the output should also be 0. Next comes the slew rate. Now, by slew rate, what we want is, we want the potential at the output terminal to switch from 0 to the maximum limit in least amount of time. And in ideal cases, we want that time to be 0. Now, if we want this time to be 0, we are basically wanting our slew rate to be infinite. So, slew rate should be infinite in case of ideal op-amps, because ideal op-amps output should reach from 0 to plus Vsat in 0 amount of time. Then comes the common mode rejection ratio. Common mode rejection ratio, as the name suggests, should reject the common input voltages that is being applied to both the input terminals and amplify the difference between the two voltages, as we had seen in this point number 5, that if we are providing the same potential, then the output should be 0. It should amplify only the difference between the two terminals. Now, these were some of the characteristics, that input impedance should be infinite, output impedance should be 0, gain should be infinite, bandwidth should be infinite. When Vin is 0, Vout should be 0, slew rate should be infinite, and CMMR or common mode rejection ratio should be infinite. Next, let us compare our ideal and practical op-amps. Now, in ideal cases, we wanted our gain to be infinite, but in practical scenarios, the range which is available is 10 to the power 5 to 10 to the power 9. Next comes the gain bandwidth product. Now, in ideal cases, since both gain and bandwidth are infinite, therefore their product is also infinite. But in practical scenarios, it ranges from 1 to 20 megahertz. Next comes the input resistance. Now, in ideal cases, what we had read was that this input impedance should be infinite. But in practical scenarios, the range is from 10 to the power 6 to 10 to the power 12 ohms. Last is the output resistance. We wanted this output resistance to be low in case of ideal op-amps, but in real op-amps, it ranges from 100 to 1000 ohms. Next comes the voltage transfer characteristics. Now, at the vertical axis, we have our output voltage, and on the x-axis, we have the difference between the input voltages, that is V1 minus V2. Now, as you can see, that the range where the op-amp is working as an amplifier is very limited. So this is the only range, this is the only part of VD, this to this, where it actually works as an amplifier, because after it has crossed this limit and it reaches somewhat here, then it provides a constant voltage of VCC or minus VCC. These are basically the power supplies which we are applying at the plus V and the minus V terminals. So this is all about operational amplifiers. I hope you understood. Thank you so much.